I will speak only for myself this afternoon. I don't speak for the CASAC, much though I enjoy and feel privileged to work with the other CASAC members. I don't speak for EPA, nor for the Society for Risk Analysis or the Journal. I'm just going to tell you what I think about some of the most important topics in the intersection of science and policymaking, where the goal is to figure out what works in making people healthier. And I do, given the whole nature of our time together yesterday and today, I do want to look some at proposed fixes as well as at what I think needs fixing. The underlying goal is to make regulatory science more trustworthy. What I mean by that is I see many claims, even dramatic claims, about the enormous benefits from often tighter regulation. My favorite example is an estimate by the EPA from a few years ago that assessed something like $2 trillion per year in benefits. That's trillion with a T. From healthier people because of reduced fine particulate matter pollution. And that seems such an extraordinarily large number to me that I wondered at the time, before finding out much about the field, can this possibly be correct? And digging into it a little bit, I found in an appendix, in a table, in a note on one side of the table, that it was based on the assumption, so far unproved, that the fact that people have generally been getting healthier and healthier over the last several decades, and in general pollution has been going down over the last several decades, there's an assumption that the latter caused the former. And on that basis, large benefit estimates flow. Well, about 5 or 6 years after I wrote a paper, I wasn't yet editor-in-chief of Risk Analysis, so I sent it off to my favorite journal, Risk Analysis, and they published it. It was a paper on re-examining the basis for our beliefs in the benefits of cleaner air. And I live in Denver, where we are sometimes visited by a brown cloud. I love clean air. If all we ever did was to say, let's vote for clean air because we like it, I would have spent less time than I have on the science of fine particulate matter. But it bugs me when people say, let's vote for cleaner air because the current air is killing people. That bothers me. I want to know whether it's true. So I did some back-of-the-envelope calculations saying, suppose we take untested assumptions behind this benefit assessment, and suppose we assign to these uncertain assumptions, including the causality one, probabilities. What's the probability that's correct? Suppose it's 50-50. Suppose it's something else. And with these simple back-of-the-envelope calculations, this is, again, before learning much about the field, I concluded that there was probably a bit more than a 90% chance that the net benefits of the Clean Air Act amendment were negative rather than positive. I wasn't sure my calculations were correct, but I was sure that policymakers were not being informed when they heard numbers like $2 trillion per year that, well, it might be that, or it might be, and probably is, negative. They weren't being presented a range of values with probabilities that looked at the full set of uncertainty. This, to me, would be an example of a claim that is not on its face trustworthy. On its face, it inspires one to wonder what the heck is going on here. Can it possibly be true? So, as it turns out, I've had the chance to dig into this literature considerably since then, and have in the last couple of years had the wonderful opportunity to work with the CASAC in advising EPA. And in doing that, I've thought a lot about, well, what should we change so that the estimates of risk really are trustworthy? When you see them, you know that if you check them out, they will check out. So the problem with air pollution, although it's the one that's occupied a fair amount of my service time, as I think of it recently, is part of a much bigger problem. I quote here from a bulletin put out by NIOSH a couple of years ago. NIOSH, to their credit, decided to write down how they think risk analysis should be done to help people do it that way. I disagree with many of their recommendations on how risk analysis should be done, but I think it's exactly the right thing to do, to write down explicitly, here's how we think you should do it. So they say, furthermore, data from most studies are imperfect. I find myself in strong agreement with that, and potentially incomplete. Well, in my observation, they're almost always incomplete. So yes, I assent to that. Therefore, I'll leave a question mark hanging over the therefore. Therefore, models may require a number of assumptions based on scientific judgment. Is that right? Is that the best way to deal with missing data or uncertain models? Well, let's leave that question hanging. The choice of modeling approach can markedly influence risk estimates. Yes, they can. The risk estimates can stop being zero and start being positive, for example. Very pertinent example. Moreover, limitations in available data, which I think there's something in the Bible saying limitations in available data you will always have with you. Limitations in available data often require, what do they require? Scientific judgment again, in order to fill gaps in model specifications. So I think this is a non sequitur. I grant the premise, which is there are many imperfections in data. But I was trained as a statistician. I'm very familiar with really ingenious and numerous constructive ideas for using data to respond to limitations in the data. So there's a lot of fancy methods for what do you do when you have missing values? Well, can you impute them? Can you impute them multiple times because you might get it wrong? What do you condition on? Suppose there might be hidden variables. Can you test for the presence of hidden variables? Can you do latent data analysis? There are whole books written about what do you do when the data is imperfect. And only in regulatory circles, well, perhaps not only in regulatory circles, but at least in regulatory circles, the reflex, well, let's use our judgment. When all else fails, good old judgment will fill in. Not really. I mean, I think I'll position myself at one end of a spectrum, which says that objective data-driven science that can be reproduced by anyone and that does not involve judgments is possible. I have a lot of colleagues whom I like and admire who disagree with me on this, but I'll put myself on the yes, objective science is possible. And I'll try to explain a little bit of what I mean by that. Unfortunately, what analysts often convey to policymakers and to the public is, we looked at the data and here's what the data said. What would be more revealing would be to say, we looked at the data and we made a bunch of assumptions, and here's what the combined assumptions and data said. And in fact, if you vary the data wildly, you still get the same conclusions. In fact, if you just take out the data and replace it all with random numbers, you still get the same conclusions. It's actually the assumptions that are in the driver's seat. So conclusions that are driven by untested assumptions are generally reproducible. It's easy, once you know somebody else's answer, to find a set of assumptions that seem to you to be plausible, good assumptions, praiseworthy assumptions that will lead you to pretty much the same answer. And Bob's your uncle. There's another publication, and everybody's happy. Okay? Policymakers and the public are, if we're going to be able to trust science, we need to be able to trust that if an independent observer, possibly with very different political passions and ideologies, were to carry out not only the same analysis, but were to ask the same question and try to answer it using other legitimate analyses on the same data, that person would reach the same conclusions. And I don't think we're there yet. NIOSH is not alone. In my home field now of what EPA is doing, here's something from again, 2018, but reaffirmed more recently. In the evaluation of the evidence generally being epidemiological studies with some animal studies and some controlled human studies. In the evaluation of the evidence, determinations are made about causation, not just association, and are based on judgments of aspects, such as the consistency of evidence. Now, for evidence here, think association, statistical association. The consistency, the strength, the plausibility. And remember, the less you know, the more seems plausible, right? And other criteria. Ladies and gentlemen, what I'd like you to think about is that none of these is actually a criterion for causality in the only sense that matters, which is if you reduce exposure, will effects be decreased? Consistency of associations doesn't tell you that. Strength of associations doesn't tell you that. Biological plausibility of associations doesn't tell you that. What does tell you that is, did you ever try reducing exposure? What happened? And often the answer is nothing. even though there were strong associations. The US is not alone. We're not the worst, from my standpoint. The worst that I know of comes from a WHO effort, which said, to hell with data, we'll just use the BugSat model. BugSat is a bunch of guys sitting around a table. BugSat. Guys here is a non-gendered term. In the BugSat model, you get the right experts in the room, and they make up what they think is the way the world behaves, and then you put that into a computer, and you use it ever after for policy purposes. And most stunningly, refer to what you've just done as providing the scientific basis for formulating policy. Now, I've heard this word scientific used. I've heard my own views described and read my own views described as being an attack on science. And that stung because I love science. So I thought, well, what does that mean? What is science? Is there anything that we can agree on? Because clearly the people who think I'm attacking science have a different idea of what science is. I think I'm defending it. What is science? Well, I think the ultimate definition of science is that it subjects predictions to the test of data. That's what science is. Not to the test of opinion, not to the test of consensus, not to anything less than when you try out your prediction in a new setting that you haven't tried before, does it work empirically? This, to me, is what good science is about. I think this is a disastrous retreat from science when you start putting your opinions in a model and then using it as the basis for policy. That's not science. So what's wrong with judgment? Why am I so passionate against judgment? An explanation I've read many times is there's a secret plot by the Trump administration to kill babies and old people, and I'm good with that. That's my primary motivation. I call that the Darth Vader hypothesis. But no, actually it's not any latent Darth Vaderism, as far as I'm aware, God bless you, that leads to my opposition to judgment, is that it doesn't work very well. There are good people who have written entertainingly and cogently about empirical experiments, which we try out to see how well do expert judgments work. And the answer is, for the really great experts, the pundits who are often seen on TV in a wide range of areas. Many of these have to do with the stock market and politics and wars and so forth. But a very consistent finding in many different domains is that great experts are only slightly less bad than random guessing. So Philip Tetlock, who's this book, Super Forecasting, that he wrote with the Canadian journalist Dan Gardner, a very good writer, I think, sets forth some evidence from the Good Judgment Project on what does it take to become a good probabilistic estimator. And a takeaway from that book is most of us aren't good probabilistic estimators. It's not that you can't learn the skill, but you can't learn it in a few hours. It calls for a bunch of habits of mind, including treating even your best opinions as provisional. Everything is always being tested, looking for diverse sources of data. Read the book if you're interested in this kind of thing. It's a quick read. But the punchline is, well, no, judgment is not very reliable most of the time. And other people, including Danny Kahneman, have noticed the same thing, that judgment has the satisfaction that it feels right, it's quick, it's easy, gives you a chance to get together with your friends if you're on a government committee. So there are a lot of good things about it. But actuarial accuracy is not, in science or out of it, a prominent feature of judgment. It also promotes nonsense. You can ask people to give you probabilistic estimates for the birthday of the current king of France. And if they don't know that there is no current king of France, they'll come up with answers, right? So it has bothered me that the US EPA for more than 10 years has been engaged in communicating about risk in ways that appear to me to be clearly nonsensical, in the sense that they have no unambiguous sense. So one of the most important words bandied about is the word causal. There's some other terms, likely to be causal, for example. There are no terms of the form not causal, but nobody has clearly distinguished. When you say causal, do you mean that exposure is a necessary cause? You probably don't mean that. Do you mean it's a sufficient cause of early death? Well, you might mean that, but you probably don't. Do you mean it's a contributing cause? If so, would it be relevant to ask how big is the contribution? Or do you mean something else completely different? Maybe it's a predictive cause, what econometricians call a Granger cause. There's lots of things it could mean. Nobody knows what it means. I think it is literally true. Neither the people writing it, nor the people advocating the use of the causal determination framework, nor the people reading the results have the least idea what causal means at the level of, is it necessary, sufficient, contributing, or something else? All right. So, dang, should we really be basing our regulations on things that nobody understands? This is not a science problem. In a sense, this is a rhetoric problem, to go back to a discussion yesterday. Every sophomoric discussion begins, let's define our terms. We haven't defined our terms in this area where hundreds of millions of dollars at least are at stake. For your pleasure, I've cut and pasted some details on the definition of causal from a standard table that goes into the reviews of fine particulate matter and other criteria pollutants. And it gets off to a good start. Something is considered causal if the evidence is sufficient to conclude that it is causal. This is what you may be familiar with as a circular definition. But cutting to the chase, if it's not due to confounding and it's not due to other biases, pretty much, I mean, who knows? There's no certainty here below, but if you're pretty sure it's not those, and it's not due to chance, so let's hear it for p-values, maybe. In that case, what's left? Causation. Right? No, not right. First of all, let's just run through a common sense test. Suppose you notice that college tuitions have been going up and the climate has been getting warmer. Well, it's a significant association. It's probably not due to chance. There are no plausible common causes that I know. It's probably not really explained by confounding. And I don't think any of these are biased estimates. They seem unbiased to me. Therefore, according to this definition, rising college tuitions is a cause of climate change, right? No, not right.
It's the opposite.
yeah, right. Reverse causation, exactly. So there's something wrong with that, and I'll come back later. But coincident historical trends. There is a tradition in the social sciences, what it was called quasi-experimental design, going back to work of Campbell and Stanley in 1963, that tried to take seriously the idea of if you can rule out other explanations, then causality is what remains. So that was the refutationist approach. And Campbell and Stanley, these social scientists, developed a list of 11 standard threats to internal validity. Internal validity meaning, does your causal conclusion follow for the data that you're analyzing? External validity deals with generalization. Does the conclusion hold more widely than in the data that you're looking at? From 1963 onwards, we've had pretty good approaches to internal validity, and from 2013 onwards, pretty good approaches to external validity, but that's cutting edge stuff. The first of the standard threats to internal validity is history. History means coincident trends, and that's not one of the things that EPA even mentions in getting at causality. It makes it too cheap to get at causality, and it's the wrong kind of causality. Philosophers sometimes speak of manipulative causality, and economists of interventional causality. That's what policymakers care about or should care about, is the kind where if you pass an expensive regulation that reduces exposure, so you manipulate exposure, that causes ill effects to decline. That's what we care about, right? That's not the kind of causality that we get at when we start saying, well, if it's not chance, it's not confounding, it's not bias, it must be causality. Well, no, it's not the right kind of causality. I don't mind people calling it causality, but they should call it wimpy causality or Hill causality. That would be fine. But it's not manipulative causality. So current regulatory risk assessment practice, as I understand it, has a wonderful template. It's wonderful because it has universal applicability. Step one is to worry. Do your socks cause cancer? Details at 11. Then predict. Wearing socks causes cancer. You come out with the prediction. Well, I mean, nobody would take you seriously if you said that, so you need to do a little bit of work. The first thing you do is you divide one thing by another. How many cancers were there in the state of Alabama last year. How many pairs of socks were worn in the state of Alabama last year? If you divide one by the other, you'll get a positive ratio called the slope factor. Okay? Now you're in business. That's enough to get a headline saying wearing socks linked to cancer. The link in this case is you ran a regression analysis or computed a ratio. Nobody's saying it's a causal link. They're just saying it's an epidemiological link. It gives room for concern. One should think that the CDC would want to invest some dollars in exploring this link, which, while not yet established as causal by science, affects a large number of sock-wearing people. All right? Okay. Now that you've gotten that far, you need to convene a panel of anti-sock activists and ask them, do you think this link is causal? So none of them knows what causal means. They don't distinguish between necessary or possible or any of the other stuff I've talked about. And after a while, some of them are going to say yes. And if they don't, you can say, do you think it might be causal? And here's $10 million if you think that this is causal enough to be worth further study. Right? Okay. So yes, a judgment is made. That judgment may be, with the prevalence of sock wearing lower than ever in the state of Alabama, still we find this positive ratio of cancers to socks, right? So you can always do this. Then you present the quantitative information to Congress and you say what we need to do is cut back on socks. This is cancer is a serious disease. You're not going to save lives. All you have to do is regulate socks. Of course, I'm being silly, but not really, because this logic is the logic that's used in serious examples. It's used for air pollution. It's used for things that matter. And it's no better than silly examples. It doesn't follow from the fact that you can run a regression analysis or construct a ratio or ask people for their opinions. That's not how you get at the truth. It obviously doesn't work for socks and cancer. It doesn't work better for other things. So, interpreting associations causally leads to dramatic predictions and calls for action. Here's an example with estimated benefits in decreased heart failure hospitalizations from tighter particulate matter regulation on the y-axis and median daily PM2.5 concentrations on the x-axis for a whole bunch of states. And the author's conclusions are that, as you see, increases in particulate matter are bad, and cutting it back would prevent 7,978 heart failure hospitalizations per year and save $333 billion US. So this is typical. I picked this as an influential paper. This is typical of what policymakers say. Obvious confounders, such as could it be that poorer places have higher pollution and higher mortality, are not accounted for. Although it talks about increases in particulate matter, no actual increases ever took place. They're talking about differences and interpreting them as changes, but they're not changes. We've made the miraculous leap from association to prevention, but you can't get from association to prevention. All right. Here, instead of using lots and lots of observations, I've used just a few. 3 communities, concentrations of 4, 8, and 12, mortality rates of 8, 16, and 24. And by the way, the poorer communities in my example do have higher concentration rates. The question we want to answer in an example like this, or in a large-scale real example, is how would cutting exposure concentration affect future risks? The point I want to communicate to you is that there is no way, even in principle, to answer that question from this kind of data, even though that's in fact what people claim to do. So for those of you who like a little mathematical entertainment with your lunch, or post-lunch, here are 3 models. In model 1, the risk is simply twice the concentration. 8 is 2 times 4, 16 is 2 times 8. In the second, the risk is 35 minus 0.25 times the income, minus 0.5 times the concentration. If you run the numbers quickly in your head, you'll see that they work. And model 3 is, actually concentration has nothing to do with risk, it's just 28 minus 0.2 times the income. So depending on which model you fit, you can conclude that there is a positive association or a positive effect of concentration on mortality, or that there's a zero effect, or that there's a negative effect. If there's money on the table for research, which of these would you prefer to publish? Well, unfortunately, this kind of model-dependent conclusion is not an adequate basis for policy. We need to do something better. The something better, or one of the something betters, is to say, so what's the graph? What's the model? What points into what? What depends on what? Can we get at that from data? And ladies and gentlemen, in many cases, the answer is yes. We can use objective methods to find out whether we can confidently reject the null hypothesis of no dependence between two variables. That's called a conditional independence test. Now, in fairness to everyone, I still have 4 minutes and a little bit. Just enough time to dwell on the loveliness of conditional independence tests. But instead of doing that, I'll raise the philosophical question, should we be betting important policy decisions and costly policy decisions on anything less than robust conclusions that are not driven by untested assumptions, that are not model dependent? So my points so far are that regulation and also litigation commonly misinterpret association as causation, but it isn't. So yes, who has standing is often a potent argument, as it was just the other day. Let me say the current method, which I've briefly described, does lead to exciting headlines. Not always consistent headlines, but exciting headlines. Millions and billions and trillions of people are dying. and you can prevent it by regulating whatever we want to regulate today. What the headlines don't communicate is, first, it's impossible for there to be X million extra deaths per year from anything unless there are X million extra births per year. There's just arithmetically, you can't do it. So this can't be right. And secondly, model dependence is generally not emphasized. And thirdly, the fact that the total number of deaths don't add up to 100% of deaths. They might add up to 1,000% of deaths. That's generally not emphasized, although it's well understood by epidemiologists, but not by most other people. But I read things like this in U.S. news from last year. 100,000 Americans die from air pollution, study finds. My first thought is, no, they don't, not each year. I can guarantee you, unless air pollution has the remarkable property of retroactively increasing the birth rate one lifetime ago, right? Which is not a generally conceded health effect of air pollution. I'll leave that as it is. So association is not causation. This article quotes the author is saying the link between fine particulate matter. Ladies and gentlemen, if you don't remember anything else from this talk, remember, whenever you see the words "the link," clutch your wallets. There's something bad going down. The link is well established. Our work builds on that. In other words, we're going to assume that association is causation. And nuts to people like me who say that the causal relationship actually hasn't been established. It has not been established. There are lots of studies that look at it. They don't find it. How can we do better? Even I can't pretend that there's more than 45 seconds left. How to do better in 45 seconds? Basically, apply the scientific method. The scientific method says make unambiguous generalizations from past data and then test them with data not used in making the generalizations. And how do we do that? I'll give you a couple of examples. There are two kinds of testable predictions. For time series data, are risk reductions greater where exposure has decreased than where it hasn't? That is a testable question. And for cross-sectional data, does risk depend on exposure after accounting for other things? Again, a statistically testable proposition. Here's an example of a moderately famous study, the Dublin intervention study, where coal burning was banned in Dublin. And Dockery of the Harvard School of Public Health noted that black smoke in air and also sulfur dioxide measurably declined from the few years, 6 years I think, prior to the ban to the few years after. This looks like a pretty good design. We're actually going to collect data before and after and look for differences. More excitingly, Total mortality rates declined significantly from the years before to the years after, and even more specifically, cardiovascular diseases had a significant drop before versus after. Going back to Campbell and Stanley, 1963, what was the first threat to internal validity? History. So some darn fool methodologist said, well, actually, if you're just looking at the time series and you don't know the hypothesis you're testing, you'd have a hard time figuring out from the time series when that intervention took place because it didn't make any difference, right? And then some other methodologists said, yeah, and also you didn't use a control group. And your mother wears army boots, so go use a control group. So the HEI funded Dockery and co-authors, and they came back in 2013 and said, actually, never mind. I mean, they didn't say never mind. What they said is, well, we can find respiratory health effects. But that's multiple testing bias. They hadn't originally claimed that. Cardiovascular, which they had claimed, went away. More importantly to me, total mortality went away when they used groups. So they should have done that up front. Dublin is not alone. Last year comes a meta-analysis of 42 studies assessing 38 unique interventions. They come out at the same place, which is actually darn hard to find an effect. It's hard to find a clear effect. Now, I've done some power calculations that say if there were an effect of the size that has been estimated based on associations, it should be dead easy to find, because these are large studies. Okay, we're in the home stretch. I no longer quote minutes and seconds because it becomes embarrassing. But there is a way of visualizing dependence relations among variables. What's going on with these arrows is we can say, here's PM 2.5, here's cardiovascular mortality. On what does cardiovascular mortality depend? Ideally using non-parametric tests. And we look at the arrows that point into it. It depends on month, it depends on season, it depends on region. And on what does PM 2.5 depend? It depends on region. Oh, they both depend on year. But the really important thing is there's no arrow directly connecting PM 2.5 to cardiovascular mortality. There's no, and I would say, not everyone agrees with me, I would say you just flunked the first screen for real causality. If there's no effects depend on their direct causes. They do. Otherwise, we're not talking about causality in any sense that I care about. All right, so conclusions. Science, I think, is a process, or should be a process, for discovering and validating and refining general causal laws, predictive causal laws, using reproducible data. It can help us to challenge and to replace false assumptions. It can help us to get at the truth from data. This is what, and also to develop the concepts for describing the truth. This is inspiring stuff. Since Galileo, it's been exciting to many of us, partly because of the surprises that it delivers. What it can't do is these things. It can't tell us what does sound science tell us we should do? The answer is sound science is silent on the topic of what should we do. What should we do is a policy question. Secondly, it doesn't actually tell us who or what is how much to blame for things, although many folks think that it can. It doesn't reveal the unique probability of an event. All probabilities are conditional. Safe to say, well, what information are you conditioning on? But it can help to detect dependency relations. It cannot make expert judgments trustworthy, although it can substitute for expert judgments. Now we're learning from the real world. It cannot manufacture useful certainty from ambiguous data. That's not something that real science does. It annoys me when I see the scientific consensus about something is something. That's really going beyond science. Consensus is a political construct. And it cannot predict the effects of policy changes from associations. And when it is presented as if that's what science we're doing, you're not being fed good science. To fix what's broken, start clearly defining what we care about. How much reduction in risk will there be from a reduction in exposure? Prove it. There are many places in the world where exposure has been reduced and other comparable places where it hasn't or where it's gone up. So use the data. Use causal methods for causal questions. Stop treating association as causation. stop treating judgments as science. That's my four-part recommendation for what we can do to make things a lot better than they are right now. Thank you for your stamina and attention.
Fascinating talk. Thank you very much. Liked almost all of it until the very end. Almost the very end. Your first recommendation was science does not imply policies.
Yes.
My background is economics, and there are certain laws in economics that predict certain things. And when political laws are passed that violate those laws, economists can and do predict certain results. And that's suggesting policy to me.
Yes, I think the constraints imposed by sound science should be very useful in guiding policy. This is what I want. When I say how can we make regulatory science more trustworthy, I want it to be trustworthy for guiding and constraining actions. So I completely agree with you that if you're trying to take actions to achieve certain goals, such as protecting public health, then you should respect the causal constraints that science gives you. All I'm saying is that science does not tell you what your goals should be. It tells you how you can achieve varying goals, but not which ones you should try to achieve. Right. Jennifer.
I'm so happy to see all these people from the rest of the United States here. And I would like you to think about how many trends have started in California in this environmental space, and then the fact that they spread, even though there might be some initial disbelief at the possibility of their spreading, and tell you about the newest one, which is the concept of defining a vehicle mile traveled in a passenger vehicle or pickup truck as an in and of itself adverse environmental impact. Even an electric car, even on an existing road, even by existing residents. It's an adverse impact. It's critical to reduce vehicle miles traveled to solve global climate change. And that's from the California Air Resources Board, which tracks back into we should all live in small, high-density apartments and take the bus as the policy outcome. These are now legal truths adopted in law and regulation in California. I've got a civil rights lawsuit pending against these because the people most harmed are those typically browner and younger people who have to live further away from their jobs because they can't live anywhere closer because of housing prices. Do you want to even start to think about what a vehicle mile traveled metric looks like in the world of science? Because there are some of us who would welcome any advice.
Yeah. In a way, I think that goes back to the preceding point, which is it would not have occurred to me to set as a goal reducing vehicle miles traveled. But science doesn't give us goals. What science will do is to say, if you want to reduce vehicle miles traveled, put a huge tax on cars or whatever. So no, I don't feel I have relevant expertise to say anything useful other than we're squarely in the realm of policy, which can be informed by, but is not dictated by science.
You assume that there is a one-to-one relationship, but let's say you go into two different populations on Earth. And in one population, yes, but there may be genetic predispositions, for example.
Those will be other variables.
But do you account for that?
In order to define causality, you'd better account for it, yes. And then to be constructive. Now this is an area that is a mile deep technically. So we're talking about what really is a causal relationship. And a useful model for a causal relationship is the conditional probability distribution for the variable that we're looking at, given the values of its direct parents in a causal network. The idea is if this is really a causal relationship, that conditional probability table should be the same no matter what data you use to construct the causal network. The causal relationship, if it's a genuine causal relationship, is invariant across different settings. If you're missing something such as genetic predisposition, so there's a latent variable that affects the observable outcomes, under certain conditions, not always, but under certain conditions, we can detect and model the effects of latent variables. And it is important to do so. Otherwise, you're not looking at a causal relationship. You're looking at an unknown mixture of causal relationships. So this is the tip of a very large statistical iceberg, but it is important.
Absolutely, because you're also the problem with causality is that how coupled the variables are.
Yes.
If they are very highly coupled, then you're looking at Granger causality.
Yes, yes, yes.
Otherwise, you're looking at dynamical causality.
Yes. And again, a big iceberg beneath this tip, one of the practical challenges. So I annoy some people. It's unbelievable, isn't it? But I annoy some people by maintaining that, in my opinion, the most desirable and also a practical way to do epidemiological science is to drop data into a powerful set of software routines, push the button that says go, and wait to get the results. So I believe in completely automating the process of inference and interpretation. Many people that I like and admire really strongly disagree with that. They say you can never take the human out of the loop. And that gets into a discussion, why can't you take the human out of the loop? What is it that's magic? Is there something about life that is more than chemistry? So anyway, I do believe that in practice, this ideal of dropping all the data into a wearing blender, pushing the button, seeing what comes out of it, we're substantially down the road of being able to do that with things like conditional independence tests. But I acknowledge that timing is a huge issue. If you collect data that's too far separated when you're studying a dynamical system, there will be a lot of false positives in the causal network that's learned from that data. And so I consider myself an advocate and champion for the practical application of what I would now call modern causal methods, going back roughly 100 years. I acknowledge and applaud and draw on the work of pioneers who are advancing what can be done with causal analysis. Much of that advance deals with timing, and it's not yet ready for prime time.
Mr. Cox, thank you very much for the work you're doing there. Who's going to do this fixing? Or do you give seminars to the permanent bureaucracy at the EPA?
Not when they can help it. I think the practical work of fixing, look, there's the frontier of expanding the set of stuff that we think we know how to do. And then there's practice, which is way behind that frontier. In my, what I consider service work, and it makes me proud to try to make things better for regulatory science. In that work, just getting people to define their terms. Do you mean manipulative causation? Do you mean necessary? Do you mean sufficient? What are you talking about? Because I really care. Getting people to define their terms, getting people to test predictions against data instead of using judgment. If I could have those two wishes, neither of which is anywhere near the state of the art, I mean, this was old when I was young, I would feel I'd done an incalculably large service for our country. So I think your question is excellent. And yes, by the way, I do give seminars now and then. People invite me. I can't say I've never been invited twice, but I've been invited once many times. And I enjoy proselytizing what I think are powerful principles for getting at truth through data. I mean, this to me is really exciting. That's not where the biggest need is. The biggest needs are recognize what people have known for a couple of decades now about the limitations of judgment, and recognize what can be done without judgment, and then go do that really well. And you don't need a PhD in risk analysis. You don't need any of the fancy methods I've talked about. Those are the most important things, in my opinion.
And I'm going to say we're a little bit into our break, so.
Okay. Thank you all.